This video will be beginning the chapter of atoms and molecules. Now, atoms and molecules are part of the entire universe. When I say entire universe, whatever we see in the universe is made up of matter and energy. When we speak about matter, matter can be broken down to the smallest bit, but after a certain point, we cannot break it down any further. Okay, we come to a part of which we call as something that cannot be divided further or broken down further. Such a particle is referred to as an atom, and when atoms come together, maybe of the one element or another element, when we speak about element, I'm referring to something like aluminium, iron. These are called elements. When atoms of elements, either of the same element, come together or of different elements come together, they form molecule. In this chapter we'll cover different aspects of atoms and molecules. Let's begin the chapter on atoms and molecules. So as I said, everything in the universe is made up of matter and energy. We'll look at what exactly is matter and what exactly is energy. The entire universe is composed of matter and energy, and energy is something that gives any object the ability to do work or to carry out certain functions, whether it is uh, human or whether it is a celestial body. When I say celestial body, it could mean a sun, moon, or for that matter, an asteroid or a meteorite. Everything needs energy to work. Without energy, it would not possess the ability to do any work. The sun gives us its heat, rays, light because it possesses copious amount or large amounts of energy. We can do work, we can speak, we can sit, we can stand, we can walk because of energy. So energy is part and parcel of the universe. What is matter for that matter? Okay. Now matter is something which we call something that has got mass and occupies space. For mass meaning has got some weight. So and occupies space meaning, yeah, it occupies some area. Like we. Now where we are standing, we are occupying that particular space, that particular region, area. And obviously we have some weight. So we are also composed of matter. So matter does not just mean things that are in flesh. It can also mean gases. Gases are also part of matter. You will say, do they have mass? Do they have weight? Yes, of course they do have. They're not as heavy as us, but they do have weight and they do occupy space. See, the universe is made up of a lot of gases. Okay, so the area that we may not be able to see those gases doesn't mean that they are not occupying the space. They are there, okay, and they occupy space and they are part of what we call as matter. Now matter is composed, as I said at the beginning of this video, composed of very tiny small particles which cannot be broken down further. Such particles is what we refer to as atoms, but they retain their physical and chemical properties, and we'll look at that in as we go along this video in this chapter. Now, to put forth or to explain energy, matter, atoms, and molecules, some law had to be established, a universal law that would kind of fit a rule like that would fit for everything that is there present within the universe. So the scientists came up with laws of chemical combination, which was further divided into two more laws, which we'll see now. Before we go to laws of chemical combination and see what exactly they are, we need to understand for any thing that happens in the unit, there is a chemical reaction that takes place between the chemicals. When they react with each other, they give you a product. Those which react together are called reactants, and what is given as a result of their reaction is referred to as the product or products. If one product is formed, then a single product, or you may have more than one product, then we refer to them as products, okay, plural. So remember, in a chemical reaction, chemical substances react with each other to give you one or more than one product. Now, chemical reaction, certain changes do occur, okay, and those reactions can be physical and as well as chemical. When we speak about physical changes, it could be with respect to the amount of that particular chemical, physical, how much it is utilized. It could be the change in color, the change in the quantity, how much gas is given out. That's what we call as evaporation. Sometimes insoluble solid is formed. That means a solid that does not dissolve very well in the liquid. That is what we call as precipitation. Okay, or sometimes heat is given out, smoke is given out. Okay, so these are physical changes. Chemical changes, of course, that will happen because two chemicals are reacting with each other. So the laws of chemical combination were laid down by the French scientist Antoine L. Lavoisier. And let's see what he laid down. So he put them down as two different laws under the law of chemical combination. One he named as a law of conservation of mass, which actually follows the law of conservation of energy. Now, I'll come to that when we discuss law of conservation of mass. And the other one was the law of constant proportion. So let's have a look in the next slides. What are these two laws referring to, discussing, or talking about? Coming to the law of conservation of mass. If we recall law of conservation of energy that we have been studying when we studied about matter, okay, what is law of conservation of mass? What is law of conservation of energy? It says that energy can neither be created nor destroyed. It can only be transformed from one form to another. In other words, we cannot create energy, neither we can completely destroy energy. Energy can be transformed from one form to another. For example, we can convert, we have learned about changing from mechanical energy to potential energy, or from potential energy to mechanical energy. Not only that, we can convert heat energy to electrical energy, and we can convert electrical energy to heat energy. So many applications are there of this. We use the burning of coal to generate electricity, that is heat to electrical energy, and we can use electrical energy to produce heat. That is what, if we have an induction cooker in the house, that's exactly, or a rod, or we have a geyser, that geyser has a rod inside, so we switch on the electricity passes heat through, heats up the coils within that geyser, and we get hot water. So different aspects, different this thing. Light is also a form of energy. We get in the through light we can see things, but light also provides energy to our ecosystem as well on planet Earth and elsewhere as well. Now, coming to the law of conservation of mass. The law of conservation of mass is similar to the law of conservation of energy. That's the reason I had introduced the law of conservation of energy over here. What does the law of conservation mass say? It says that the law states that mass can neither be created nor destroyed in a chemical reaction. Similar to how we have said in the law of conservation of energy, energy can neither be created nor destroyed. It goes on to say that total masses of reactants is equal to the total masses of products and the masses of unreacted reactants. So this statement, this last statement that we have just read here, we'll just see with the help of an example what exactly is it trying to tell us. So example, reaction of carbon with oxygen to produce carbon dioxide involves conservation of mass in the following way. Let's see what it is. So carbon has a mass of 12 grams and oxygen, a single atom of oxygen has a mass of 16 grams. But because there are two atoms which we see of oxygen, since it says O2, so 16 plus 16 is 32 grams. So a single atom of carbon possessing or having a mass of 12 grams reacts with two atoms of oxygen having a mass of 32 grams total. When these two react together, we get carbon dioxide, which has a mass of 44 grams. If you have a look, if you calculate 32 plus 12, we get 44 grams, which in other words is trying to tell us that the mass over here, it has not been created, it cannot be destroyed, nothing is getting wasted over here. The total mass remains at the end of the reaction in the form of products. The product is having a mass that is equal to the sum of the masses of the reactants in that particular chemical reaction. Okay, so remember, so this is what the law of conservation of mass says. Let's go to the next one. Law of constant proportion. So we've learnt law of conservation of mass. Now law of constant proportion. According to this law, in a chemical reaction, the elements are always present in a definite proportion by mass. It is also termed as the law of definite proportion. And the example given over here is ratio of hydrogen and oxygen in water obtained from any source is 1:8. That is 1 gram of hydrogen and 8 gram of oxygen together make up 9 gram of water. I'll just explain this thing so that you have a better understanding. Okay. Now, I had in the previous slide, I had mentioned oxygen, single atom of oxygen has a mass of 16 grams, right? Now, fine. And we have learned that we have hydrogen over here. So, single atom of hydrogen has a mass of just 1 gram. However, what is the formula of the molecular formula of water? It is, as we know, H2O, which means two atoms of hydrogen combined with a single atom of oxygen. So in this case, we'll have to multiply this by 2, since there are two atoms of hydrogen, and we get the total mass as 2 grams of H2, right? So now H2O, when we speak about ratio, so it is basically saying 2 atoms of hydrogen to 1 atom of oxygen, 2:16. Now we know that 16 can be divided by 2, so that is 2 ones are 2, we get 1 over here, and 2 8s are 16. So in other words, we can simplify this ratio 2:16 to 1:8, and that's exactly what we get over here. Okay, that is why it says the ratio of hydrogen and oxygen obtained water is always 1:8, 1 gram of hydrogen and 8 gram of oxygen, that makes up 9 grams of water in any proportion. Now the ratio is not important. What is important is the law because of which we have actually noted out the ratio. What it's trying to say, this law, is whether you take this water from uh, your water bottle, whether you take this water from the sea, whether you take the water from an ocean, or whether you take the water from a pond or a river, or even from your water tank, the ratio or the proportion or the amount of hydrogen and oxygen that is present within that water, irrespective of where you have got that water from, will always remain the same. The proportion or the quantity of hydrogen and oxygen in water is universal, irrespective of wherever you find it, whether you find it on Earth or whether you happen to find water on any other planetary body in the universe. The proportion of hydrogen and oxygen that makes up water will always remain the same. That applies for any other compound as well. That is the law of constant proportion. Okay, so this law of chemical combination uh, try to um, make sure, try to um, kind of encompass or bring forth that universal truth that masses cannot be created or destroyed. It remains the same irrespective of the chemical reaction, and the fact that the proportion of uh, of the elements within a molecule always remain the same irrespective of the source of where they are found. Okay, so that these are the two laws that were put forth by Anton Lavoisier. Moving on, we come to our main aspect, that is atoms. So according to John Dalton, all elements, compounds or mixture are composed of some small particles which cannot be further divided into smaller particles, which we call as atoms. And one word for all elements, compounds or mixtures is matter. Okay, so he tried to put forth everything that he knew about. Basically, he tried to say that everything in the universe is composed of small tiny particles which cannot be further divided or broken down as atoms. So just like how in our body we have cells which are the basic building blocks, we also have atoms which are the basic building blocks of an element or compound. Basically basic building blocks, you can say, of the universe. They are very small and their radius can be measured only in nanometers. We'll see what is nanometers. So this is 1 upon 10 raised to 9 meters equal to 1 nanometer, or 1 meter can be said equal to 10 raised to 9 nanometer. Okay, now sometimes you also will find, instead of writing 1 upon 10 raised to 9 meters, sometimes it is also mentioned as 10 raised to minus 9 meters equal to, that's when you take 10 raised to 9 on in the numerator. From the denominator, the index or the power of 10 will become negative to show you that it's come from the denominator. So 10 raised to minus 9 meters is equal to 1 nanometer, or 1 meter is equal to 10 raised to 9 nanometer. Dalton proposed an atomic theory to put down what all he observed, and to lay down a foundation for further researchers and scientists to understand how atoms work in the universe. So what did the theory, atomic theory, comprise of? What did it postulate? Let's see. First, he said was the matters are composed of very tiny particles called atoms, which we have already gone through. These particles are too small to see and cannot be created or destroyed in a chemical reaction. Third, he said atoms of a specified element are identical in mass and chemical property. So again, he's trying to say the same thing. What we spoke in chemical proportion, that he said the quantity remains the same. Here is trying to say that the elements, wherever they are found, the property of that element and the mass will always remain the same. The chemical property of that element and the mass will always remain the same wherever it is found. Atoms of different elements have different masses and chemical. Yeah, but what he said was atoms of the same element will be the same everywhere, but atoms of different elements will vary. Each element is different, and the atom of different elements will vary. So if you find that the atomic mass, you've got two atoms and their atomic masses are different, that means they are two different elements. Okay, they are two different elements, they are not the same element. That shows you that they are, okay, there is no chance that the two atoms having different masses are of the same element. No, if they are having different masses, that means that they are of a different element. That is what he meant. Atoms combine in the ratio of small whole numbers to form a compound. What he meant was, see, we had, I'll just write this down rather than going to go back to the same slide. We had CO2 this way, CO2, and then we had H2O. What this is trying to tell you is they are always present in the ratio of small whole numbers. Okay, whole numbers would be 0, 1, 2, 3, 4, 5, 6, 7, 8. So you have a look, it's mostly always natural numbers, so it's 1, 2, 3, 4, 5, 6. Carbon over here is 1, okay, and here there are 2. Again, here there are 2. If we talk in terms of their masses, then we know carbon is 12 gram, oxygen is 16. So here, since there are two um, atoms of oxygen, so that means it will be 32, and this we can easily divide using 4 times table. 4 3s are 12, 4 8s are 32. So this is always present in the ratio 3:8, and water we know is always present in the ratio 1:8. So these are whole numbers. Next, it says the relative number and kinds of atoms are constant in a given. So this follows the law of constant proportion, which it says that the ratio of the atoms always remains the same irrespective of the compound. Coming to the naming of atoms. Now, naming of atoms, um, what we can say about this is that we try to give names. Why do we try to give names? We try to give names to identify the person, relate to the person, or identify that person. We give name to a book, we give name to a person, we give name to a living creature. Okay, sometimes we give even we give names even to uh, people who are not living. It's kind of a classification. Okay, used. So we also like have house numbers. Okay, that helps us to identify people to reach to us, and when we speak about that person uh, it can help us. Otherwise it will be that person, this person. If we have a name, we can say, okay, John Dalton, so we know, okay, this is that person, he was talking about atoms. So similarly, Dalton used symbols first to begin with to denote the elements, and he used one symbol which pertained to one particular atom. That means one particular atom, he chose one symbol, so that symbol represented that particular atom. And we have a look over here how he named over here hydrogen, this symbol, carbon is this symbol, oxygen here, phosphorus over here, sulfur here, iron here, copper here, lead here, silver, mercury, platinum, gold, so forth. Okay. Now symbols of some commonly known elements as anticipated by Dalton. So he put forth certain names, and the names of the elements were named in accordance with the place from where they were derived. So wherever they were found, a name was given similar to that place. Copper was found in Cyprus, so it was named copper, closer to Cyprus in that particular language. Then there were more people who tried to give names to these elements in whichever way they deemed fit, or they found the most possible thing. Sometimes they use the first single letter, sometimes they will use the first two letters of their name. Now what is happening is there is an association, a big association, a union you can say, of some of the leading researchers in chemistry. And whenever a new element is formed or discovered, because sometimes nowadays elements are also formed which are artificial, man-made as well, which are there in the list. These elements go through a committee which decides uh, what is the best name that we can give. They always take the suggestion of the person who has discovered it, who has made it, and then they give the approval to it. Then the entire uh, community of researchers from the chemistry background, they tend to follow it as a universal name for that particular element. So this association is called IUPAC short. The actual name is International Union of Pure and Applied Chemistry. Okay, these are the guys who assign names of these elements. Now symbols of different atoms of different elements. In fact, if you go to class 10, you will have an entire table which is called as the modern periodic table, which gives you a list of all the elements which have been discovered till the time that the book has been published, reprinted, updated. Okay, and you will see that there are so many elements over here. Now here it says 115 elements. There have been more elements that have been found since this book has been published. So you need not know, as far as your textbook says it is 115, will stick to 115. Each element has got a different letter. That letter symbolizes that element. Sometimes the starting letter of that element is used to denote it in capital letters, and sometimes the first two letters are taken, and in that case the second letter in that is not capital but small, so first letter is here. So for example, over here we see hydrogen, it is capital H. Aluminium is capital A small l, and not capital A and capital L. So it is just capital A capital. But we have also seen, we've got cobalt as well over here, but we have seen it is not always the case that they just follow this particular naming system. Okay, sometimes you'll have different naming system as well. Have a look at this zinc over here. This should have either been Z or ZI. In fact, it is none. In fact, it is ZN. Okay, So you will have, generally it follows this pattern, first letter or first two letters, but sometimes you do have, and then you also have instances where where it doesn't follow the name at all, but it follows its Greek or Latin name. Okay, that is seen in many cases. Some examples given over here is in case of sodium, which is Na. Okay, so it doesn't say S because S stands for sulfur. Okay, so you have Na standing for natrium, which is its non-English name, and you have this is iron. Its Greek Latin name is ferrous. So you have Fe over here. Then you have K, which is actually potassium. Its non-English name is calcium. Okay, and then you have many others in the similar uh, fashion. You have gold, which is Au, then you have silver, which is Ag, and then you have mercury, which is Ag. So these are not following the trend that was generalized, that is generalized over here. So these are some symbols of atoms that you will come across. You'll come across whole lot of them in class 10. For now, we'll learn only a few of them in this particular chapter. So in this video, we'll stop till here, and we have covered a good deal of what is matter and energy, and what are atoms, and the laws of chemical combination, and including naming of atom. Please subscribe to the channel and do not forget to click on the bell icon to receive further notification. And if you like the video, please click on the like button. Thanks for watching. See you in the next video.